temperature changes in a system indicate energy changes. So for example, if we isolate this system from the surroundings and add heat to it, then the molecules are going to vibrate and gain kinetic energy because the temperature of this system is going to increase. Now in contrast, if heat is expelled to the environment, then the temperature of the system is going to decrease and the molecules lose energy. So therefore the intermolecular forces become more significant and water freezes into ice. So we call this here an exothermic process where energy was lost to the surroundings via heat transfer. And in contrast, we call this an endothermic process where the system gains energy from the surrounding. And this can occur through the addition of heat or work being done on the system. If you compress this volume, then the system also gains energy. And similarly for a chemical reaction, so here you have the breaking of the bonds between oxygens and the formation of the bond with each carbon monoxide molecule. And this releases heat to the environment, so we call this an exothermic chemical reaction. The formation of a solution may be an endothermic or exothermic process depending on the relative strengths of the intermolecular or interparticle interactions. So for example, when salt dissolves in water, step 1 involves the breaking of the ionic bonds in the solute. So energy must be input into the system and equal to the lattice energy to break those bonds. And given energy is input into the system, this step is endothermic. Now step 2 involves the separation of the solvent or water molecules, and energy is required to weaken the intermolecular forces to make room for ions to react with the water molecules. So here energy is input into the system. Now in step 3, new intermolecular forces are formed between the water molecules and the ions, being ion-dipole interactions. So therefore energy is expelled to the surroundings, and this step is exothermic. And step 1 is called the lattice energy, and steps 2 and 3 are called the hydration energy. And the hydration energy is greater than the lattice energy, so therefore the net process is exothermic. A physical or chemical process can be described by an energy diagram which illustrates the exothermic or endothermic nature of the process. So for example, we have the following multi-step reaction, and starting with the energy of the reactants, once the activation energy is overcome and transition state 1 is reached, then the bonds between A and B are being broken. And at the end of step 1, you have the decomposition of AB into simpler molecules with C left over. So step 1 is endothermic because energy was input into the system to break those bonds. And when the activation energy to initiate step 2 is overcome, then the bonds between molecule B and C are being formed. And at the end of step 2, we have the energy of the products. So step 2 is exothermic because energy was released by the system when the bonds between B and C were formed. And given that the overall energy of the products is lower than the energy of the reactants, this is an exothermic process overall where energy was transferred to the surroundings. Suppose we heat up a metal bar, and therefore it has a higher temperature than the colder bar on the right. And in a metal, the electrons are mobile and gain higher velocities when we heat up the bar, whereas the electrons in the colder bar are travelling at lower velocities. And note that the temperature of the bar is proportional to the average kinetic energy of the particles. Now once we bring these bars into contact, heat flows from the hotter to the colder bar, which is a process called heat transfer, or the transfer of energy via heat, and that causes the electrons in this bar to gain a higher kinetic energy because the particles in both bars are going to be in contact with each other. And as all these particles continue to collide, thermal equilibrium will eventually be reached where the final temperature of both bars is going to be the same and no heat flow occurs between them. And the same concept applies to gases, where you have the gas particles travelling around at different velocities, and the particles in the hotter container have higher velocities than the particles in the cooler container. The heating of a cool body by a warmer body is an important form of energy transfer between two systems, and the amount of heat transferred between two bodies can be quantified by the heat transfer equation, where the heat transferred is equal to the mass of the body by the specific heat capacity by the change in temperature of the body. And this can be written in terms of the number of moles and the molar heat capacity, where the specific heat capacity is the energy required to raise the temperature of 1 gram of a substance by 1 degree Celsius or Kelvin. And similarly, the molar heat capacity can be written as follows. Now for example, if we drop a hot iron block into a styrofoam cup holding water with the following properties, and that causes an increase in the temperature and the amount of heat transferred to the water, and similarly the heat lost by the iron block, and negative because this is a loss. And assuming there's no heat lost to the environment, when thermal equilibrium is reached, we have the following condition. And you can use this condition to solve for the final temperature. The first law of thermodynamics is a statement of conservation of energy, where the change in internal energy of a system is equal to the heat flowing in or out of the system, plus the work done on or by the system. And a typical model analysed in thermodynamics is an ideal gas, and this constitutes our system that we're analysing, and everything else in the universe is the surroundings. And here we have a piston that can move up and down to do work on the system, and the heat reservoir enables heat to flow in or out of the system. So heating a system increases its energy, given that the temperature increases, and that causes the piston to move upwards by some amount, and the pressure due to the forces from the particles acting on this area of the gas volume gives the average force, and multiplied by delta Y gives the work done. So therefore this can be written as pressure by the change in volume, and therefore our change in internal energy can be written as follows. So a positive change in volume yields a reduction in internal energy. So here we covered the basics to use in this chemistry unit. Recall the first law of thermodynamics, which says that the change in internal energy is equal to the heat going in or out of the system and the work done on or by the system. So if the change in volume is positive, then the system expands and the internal energy decreases. And the internal energy is a state variable because it only depends on the initial and final state of the system, not on the process that brought the system from the initial to the final state. Whereas the heat and work are not state variables. Now a state variable that we'll use in chemistry is enthalpy, which is defined as the internal energy plus the pressure by the volume of the system. And therefore the change in enthalpy can be written as the change in internal energy plus the pressure by the change in volume plus the change in pressure multiplied by the volume. And if we substitute for the internal energy, then these cancel, and for a system under a constant pressure, and therefore the change in enthalpy is equal to the heat energy absorbed or released at constant pressure. And most chemical reactions occur under this condition. Calorimetry experiments are used to measure the transfer of heat, and under this configuration we have a styrofoam cup or a coffee cup, which is a good insulating material, a thermometer, a stirrer to mix reactants, and a loose fitting lid which exposes the reactants or bodies to a constant atmospheric pressure. Now for example, if we dissolve sodium chloride in an aqueous solution, it dissociates into ions. So before the sodium chloride dissolves in water, we have an initial temperature reading, and after it dissolves causes an increase in temperature. And the heat absorbed by the solution at constant pressure is equal to the mass of the solid plus the mass of the water, which now form the solution, multiplied by the specific heat of the solution, and multiplied by the change in temperature. And therefore the heat released due to the dissolution process at constant pressure is a negative of the heat absorbed by the solution. So therefore the dissolution process is exothermic because the temperature of the solution increased. Sodium chloride is dissolved in water. In a styrofoam cup, calculate the heat released due to the dissolution process if an increase in temperature is recorded, and the specific heat of the solution is given. Well, the heat absorbed by the solution at constant pressure is equal to the mass of the solid plus the mass of water, which is the same as 100 grams, multiplied by the specific heat of the solution, and multiplied by the change in temperature. And we typically convert this to kilojoules. So the heat released due to the dissolution process is a negative of the heat absorbed by the solution, where we use three significant figures. And at constant pressure, this is the same as the change in enthalpy. Energy must be transferred to a system to cause a substance to melt or boil. So here we represent the different phases of a substance using a heating curve, so solid, liquid and gas. So as heat is added, there's an increase in temperature because the molecules gain kinetic energy up to the melting point where a phase change occurs. And during a phase change, the temperature is constant because there's no increase in kinetic energy of the molecules. And the heat that's input, being the heat of fusion, is used to overcome the intermolecular forces, and as heat continues to be added until the phase change from a liquid to a gas, being vaporization. So as you can see, this is longer than the melting phase because it's harder to break apart water molecules compared to ice. Now going backwards, you have a decrease in energy. The enthalpy of condensation is equal to the negative of the enthalpy of vaporization. And the same thing as we keep going backwards, where the enthalpy of freezing is the negative of the enthalpy of fusion. And you'll also notice a shallower slope in the liquid phase compared to the solid phase because you need to add more heat to cause an increase in temperature. A 2.1 gram ice cube has an initial temperature of 10.3 degrees Celsius. How much heat is required to vaporize the ice completely? And we can use the following properties. So the heat required to increase the temperature of the ice to the melting point can be obtained using the heat transfer equation. We have 2.1 grams of ice and a specific heat of ice and a change in temperature. And now the heat required to change phase from a solid to a liquid is equal to the enthalpy of fusion multiplied by the number of moles of H2O, and we can convert this to a number of joules. And you can obtain a number of moles of H2O using the mass and the molar mass. And similarly, we can use a heat transfer equation to determine the heat required to increase the temperature of the water up to the boiling point. And then we can use the enthalpy of vaporization to determine the heat required to change phase from a liquid to a gas. And therefore the total heat required can be obtained by adding these together and using the correct number of significant figures. Suppose we have this neutralization reaction where solutions of hydrochloric acid and sodium hydroxide are mixed together. And after the reaction takes place, you obtain dissociated sodium and chlorine ions in solution and H2O molecules, which gives the final temperature reading. So the heat absorbed by the solution at constant pressure is equal to the mass of the solution, and for this type of problem you'd be given the volume and molarity of each solution and also the density of the solution to work out the mass, and you multiply by the specific heat of the solution by the change in temperature. And therefore the enthalpy of the reaction is equal to the negative of the heat absorbed by the solution over the number of moles of the limiting reactant. So for example, if our limiting reactant is hydrochloric acid, and to get the enthalpy of the reaction, we multiply by the number of moles of the limiting reactant per mole of reaction. And this will give you a result in energy per mole, and the enthalpy of the reaction is negative for exothermic reactions and positive for endothermic reactions. A styrofoam cup is used to mix solutions of hydrochloric acid and sodium hydroxide, and the following reaction occurs. Calculate the enthalpy of the reaction if an increase in temperature is recorded, or the heat absorbed by the solution at constant pressure is equal to the mass of the solution, which is the volume, multiplied by the density, and multiplied by the specific heat by the change in temperature. And to obtain a limiting reactant, we calculate the number of moles of hydrochloric acid, which is volume by molarity, and a number of moles of sodium hydroxide. So here you have a 1-to-1 ratio between the moles of hydrochloric acid and sodium hydroxide, so hydrochloric acid is the limiting reactant. And the enthalpy of the reaction is the negative of the heat absorbed by the solution over the number of moles of the limiting reactant, and in this problem we have 1 mole of hydrochloric acid per mole of reaction, and we convert this into kilojoules, which gives negative 64 kilojoules per mole of reaction using two significant figures. 14.1 grams of aluminium reacts with excess iron 3 oxide. Determine the amount of heat released. Well, the heat released due to the reaction is the enthalpy of the reaction, and here we have 2 moles of aluminium per mole of reaction, and then multiplying this by the number of moles of aluminium gives the heat released by the reaction. Now the number of moles of aluminium is obtained by dividing the given mass on the molar mass. So therefore if we substitute for the number of moles, we determine the heat released by the reaction using 3 significant figures. We can determine the enthalpy of a reaction by recognizing that the breaking of bonds is an endothermic process and the formation of bonds is an exothermic process. So by subtracting the average bond energies of the formed bonds from the average bond energies of the broken bonds, we can obtain the enthalpy of the reaction. And here the superscript represents standard conditions. Now here we say average bond enthalpy because these bonds can exist in different compounds. So we take the average. So in this example, we have 2 hydrogen molecules reacting with an oxygen molecule to form 2 H2O molecules. So therefore these bonds are going to be broken and these bonds are going to be formed. So therefore the enthalpy of the reaction can be written using the bond energies. So the sum of the bonds broken minus the sum of the formed bonds. So this synthesis reaction is exothermic. And note that all the molecules are in a gas phase, but if this were the liquid phase for example, then we need to consider the enthalpy of condensation. So therefore this would need to be added to the bond energies of the products, because condensation is an exothermic process. The combustion of methane is given by the following reaction. Find the enthalpy of the reaction using the bond energies, and given the enthalpy of vaporization of water, because we have a phase change. So first we draw the geometries of the molecules to get a better visualization of the bonds. And now to calculate the enthalpy of the reaction, we have the bond energies of the broken bonds minus the bond energies of the formed bonds. And we also need to subtract the heat of condensation due to the phase change, which is a negative of the enthalpy of vaporization. And given we have 2 H2O molecules changing phase, and using 3 significant figures, we obtain the following result. And as expected, combustion is an exothermic reaction. The enthalpy of formation is the change in energy that occurs when 1 mole of a compound is formed from its pure elements under standard conditions, which is 1 atmosphere and room temperature. So for example, 1 mole of water is formed from 1 mole of diatomic hydrogen gas and half a mole of oxygen gas. And these naturally exist as gases under standard conditions. So it doesn't take energy to form them. And for example, oxygen gas has an enthalpy of formation of 0. And here you see half a mole of oxygen gas, because these chemical equations are written based on 1 mole of the compound being formed from these constituent pure elements. And here is another example of methane being formed from an allotrope of carbon, and 1 mole of methanol is formed from the following constituent pure elements. So therefore the enthalpy of a reaction can be obtained by subtracting the enthalpies of formation of the reactants from the enthalpies of formation of the products. And these are typically given in tables. The combustion of methane is represented by the following reaction. Find the enthalpy of reaction, assuming standard conditions, is equal to the sum of the enthalpies of formation of the products minus the sum of the enthalpies of formation of the reactants. So for the products, we have 1 CO2 plus 2 H2O, and for the reactants, we have a methane, and the enthalpy of formation of oxygen is 0, because it exists naturally as a gas under standard conditions. We obtain 890 kilojoules per mole. And this is similar to the result we obtained using Bond enthalpies. And this is the same as the enthalpy of combustion of methane, because we have the combustion of 1 mole of methane. Hess's law states that if a reaction can be specified using a series of steps, then the sum of enthalpies of all the steps is equal to the enthalpy of the overall reaction. But first we need to manipulate these steps to match that reaction before we sum them up. So according to Hess's law, when a reaction is reversed, you flip the sign of the enthalpy. So for example here, we want to flip the reactants and the products such that acetylene ends up on the right hand side to match that reaction. So we flip the sign of the enthalpy. Now if we multiply or divide a reaction by an integer, then we can do the same for the enthalpy of that reaction. So here we have 1 carbon and 2 in the overall reaction, so we multiply this step by 2. And therefore we multiply the enthalpy by 2. And in this final step, the hydrogens match, so we don't need to do anything to this step. And now if we add all the steps, we obtain the overall reaction, and therefore we can add the enthalpies of the individual steps to obtain the enthalpy of the overall reaction, which we'll cover in an example problem. Let's find the enthalpy of this reaction given the following reactions with the following enthalpies. So here ammonia is on the right hand side, but it's on the left hand side in the overall reaction. So what we do is reverse this reaction by flipping the reactants and products. So we flip the sign of the enthalpy, and we have 1 mole of ammonia, so we need to divide this by 2. And we thereby divide the enthalpy of this reaction by 2. Now for the next step, we have methane on the right, so we need to reverse this reaction also. So we flip the sign of the enthalpy. And here we have 2 hydrogen cyanides on the right, but 1 on the right in the overall reaction, so we divide through by 2. Now if we add all these together, we get the following on the left hand side, and the following products on the right hand side. So on the right hand side, we have a total of 7 on 2 moles of hydrogen gas. And now if we cancel out a half from both sides, then the carbon solid cancels out. So we can see that we obtained the overall reaction, and therefore you can sum these enthalpies, which gives you the enthalpy of the overall reaction, using 3 significant figures.